Since the dawn of the Cold War, the world has lived under the shadow of ballistic missiles. These weapons of mass destruction have the power to travel thousands of miles, carrying nuclear payloads capable of unimaginable destruction. The technology behind ballistic missiles is both fascinating and terrifying. The journey of a ballistic missile begins with a fiery blastoff from a launch pad or silo. This initial launch phase is the most visible and dramatic part of a ballistic missile's flight. Powerful rocket engines ignite, propelling the missile upwards with tremendous force. The missile roars into the sky, leaving a trail of fire and smoke in its wake. During this initial ascent, the missile's guidance system works tirelessly to maintain the correct trajectory. It constantly adjusts the missile's course, ensuring it stays on track towards its intended target. The launch phase is a critical period for the missile, as any deviation from its planned trajectory could result in mission failure. As the ballistic missile ascends through the Earth's atmosphere, it begins to shed its various components in a carefully choreographed sequence. This process, known as staging, is essential for maximizing the missile's range and efficiency. The initial booster stage, responsible for the initial thrust off the launch pad, is the first to go. Once the fuel in a stage is depleted, the missile jettisons it, shedding the unnecessary weight. This allows the remaining stages to accelerate faster and conserve fuel. The second stage, equipped with its own engine, then ignites, continuing to propel the missile further upwards. This process of staging can repeat multiple times, depending on the missile's design and range. Following the separation of its booster stages, the ballistic missile enters the Midcourse Phase, the longest and most critical stage of its journey. During this phase, the missile travels through the vacuum of space, following a ballistic trajectory governed by gravity and its initial launch parameters. The Midcourse Phase is a tense game of cat and mouse as the missile attempts to evade detection and interception by enemy defense systems. At this stage, the missile's warhead, or payload, separates from the rest of the vehicle. This payload, often containing multiple nuclear warheads, continues on its trajectory towards the target. The separation of the warhead from the missile body makes it more difficult for enemy radar systems to track and target. The warhead itself is designed to be highly maneuverable and difficult to intercept, further complicating the task of missile defense systems. To further increase their chances of survival, modern ballistic missiles often deploy decoys during the Midcourse Phase. These decoys are designed to confuse enemy radar and missile defense systems, making it harder to distinguish the real warheads from harmless decoys. The use of decoys adds an additional layer of complexity to missile defense, forcing adversaries to expend precious resources targeting false threats. There are various types of decoys, each designed to exploit different weaknesses in enemy defense systems. Some decoys are simple, metallic balloons that create radar signatures similar to real warheads. Others are more sophisticated, equipped with electronic countermeasures that jam enemy radar signals or create false targets. The effectiveness of decoys depends on factors such as their design, the sophistication of enemy radar systems, and the tactics employed during deployment. In addition to decoys, ballistic missiles may also employ chaff and flares to further confound enemy defenses. Chaff consists of small, thin pieces of aluminum, metallized glass fibers, or plastic that scatter in the air, creating a cloud of radar-reflective material. This cloud of chaff creates a large radar signature, making it difficult for enemy systems to distinguish between the real warhead and the surrounding clutter. Flares, on the other hand, are pyrotechnic devices that generate intense heat. These heat signatures are designed to attract heat-seeking missiles, drawing them away from the real warhead. Flares are particularly effective against infrared-guided missiles, which rely on detecting the heat emitted by their targets. The combined use of chaff and flares creates a multi-layered defense mechanism, significantly reducing the effectiveness of enemy missile defense systems. To further complicate matters, some ballistic missiles are equipped with multiple independently targetable reentry vehicles, or MIRVs. Instead of carrying a single warhead, MIRV-equipped missiles carry multiple warheads, each capable of striking a different target. These warheads are housed within a bus that releases them individually during the midcourse phase. The bus maneuvers itself to ensure each warhead is on the correct trajectory to hit its designated target. MIRVs present a significant challenge for missile defense systems, as they must track and attempt to intercept multiple warheads simultaneously. This multiplies the difficulty of an already daunting task, making it extremely challenging to defend against a MIRV attack. After the midcourse phase, the ballistic missile's warhead, or warheads, enter the final stage of their journey reentry. As the warhead plunges back into the Earth's atmosphere at incredibly high speeds, it encounters intense friction. This friction generates enormous heat, causing the warhead to glow white-hot. The warhead's heat shield, made of specialized materials designed to withstand extreme temperatures, protects the warhead from burning up during reentry. The intense heat and pressure during reentry can also affect the trajectory of the warhead, making accurate targeting even more challenging. If the warhead survives reentry, it will detonate either in the air or upon impact with its target, depending on its design and intended purpose. The future of ballistic missiles and missile defense is likely to involve increasingly sophisticated decoys, more advanced radar and tracking systems, and potentially the development of directed energy weapons capable of destroying missiles in flight. Understanding the complex interplay between these technologies is crucial for policymakers, military strategists, and anyone concerned about the future of global security.